Hey guys, thanks for watching. In this video we're going to be going over the week 13 concepts for Physics 111. So starting off with simple harmonic motion, we see that this is motion which occurs when the net force on an object obeys Hooke's law. And we're going to define Hooke's law as basically this force of a spring is equal to our negative spring constant times our position. And examples of objects which would be undergoing simple harmonic motion would include a mass on a string or a pendulum, for instance. So let's take a look at these images below. Basically, we're going to step through each image and look at some of the observations we can make within that image. So basically, in this first image here, what we see is we have a mass on a spring, and this is all placed horizontally. And we see that our equilibrium position, which is going to be equal to 0, was here, and we've pulled this mass to the right to a position we're going to call X. And basically at this position X, which is going to be as far as we pull back the spring, we can notice two things. First off, our velocity at this position is going to be equal to 0, and we're going to have this force facing towards our equilibrium position. Now in the next image, we see that we've let go of the mass, and now it's being moved by the spring, by the force we noticed up here, over to the left. And basically, in this image, the object is now back at its equilibrium position. And what's important to realize at equilibrium is that our force is going to be equal to 0, and our velocity, or the magnitude of our velocity, is going to be at its greatest. And basically, what's important to realize with springs is that the forces within that spring are always going to be acting towards equilibrium. So in this case, we're actually already at equilibrium, so we don't have any forces acting on the mass. However, our velocity is going to be at its greatest magnitude, and it's going to be facing in this direction. And for that reason, in the next image, we see that our mass actually moved further away from equilibrium towards the left, and it's now at a position which we're going to call negative x. And at negative x, which is, like it sounds, the opposite of our initial position up here, we can also deduce that our velocity will be equal to 0, and we're going to have a force acting towards the right. And the reason why our force is pushing this way is because we once again want to get back to that equilibrium position. Now, that force acted upon the spring in the next image, and we're back at equilibrium. So x equals 0 here. Once again, we're going to have our greatest magnitude of velocity, and our force will be equal to 0. And then lastly, we see that once again our mass ends up at our initial position of x, and our force is going to be once again pushing back towards equilibrium, and our velocity at this greatest distance from equilibrium is going to be equal to 0. So a couple things we can now say about these images is that our amplitude, or A, is going to be the maximum distance of the object from its equilibrium point. So in this case, our A was really x. And then we can also see that period is going to be the time required for the object to move through one complete cycle. So in this case, our period would actually be all sets of this image, or of these images here, because we started off at our position x, and this is the next time we are back at position x. So basically, our period is from this image down to the bottom image. And then frequency is going to be the number of cycles per unit of time. So basically, this is what we would want to use in order to determine how many cycles we go through in a second, for instance. And this brings us into finding velocity within these scenarios. And basically, in order to find the velocity at any position, we can use this conservation of energy equation. And we're going to plug in 0 for all our initial velocities. We're going to plug in our amplitude for our initial position, because that's as far as the object is going to move away from equilibrium. And then for our heights, we're going to plug in 0 for all the heights, because we know that our object is completely horizontal, so our height isn't changing. And basically, that allows us to cancel out certain portions of this equation. And then when we rephrase the equation in order to look for velocity, we see that we get this equation here. And we can use this equation in order to find our velocity at any position. So basically, we can observe that when our x is either equal to our amplitude or the opposite of our amplitude, then our velocity is going to be equal to 0. And when x is equal to 0, then our velocity is going to be at the maximum possible magnitude. And that gives us this equation below here if we were to plug in 0 for x. That would get rid of this portion. But basically, we really just need to focus on this equation here because we can come back to these observations by just plugging numbers into the equation. Alright, earlier we defined what period was, and now we're going to look at the actual equation we can use to find the period of a spring. And that's 2 pi times the square root of our mass over our spring constant. And what we can see here is that this is going to be independent of amplitude. So if we're using the same spring and the same mass, we know that no matter how far we pull that spring back, it should have the same period because this is all independent of our amplitude. And if we look at this image on the right, we see here we have a mass dangling from a spring, and basically we're allowing that mass to move up and down with the spring. And then we also, next to it, have this paper which is being moved in this direction that I indicated. And basically what we would see here is if we were to sort of record the movement of this mass on a spring along the paper, we would see that it moves in this sort of sine or cosine shape. And basically what we can conclude from this is that simple harmonic motion is going to be the source of perfect waves. And this brings us into the pendulum. So with pendulums, when we're dealing with small angles, we're going to have a restoring force similar to Hooke's law. So in a pendulum, our restoring force is going to be equal to our negative mass times gravity times the sine of theta. And theta is going to be basically the angle of our string away from the equilibrium position here. And then we see that our period is going to be equal to 2 pi times the square root of the length of our string over gravity. And this is only going to be valid for small angles, and it's going to be independent of both mass and amplitude. So basically it doesn't necessarily matter how much mass we have hanging on the pendulum or how far we pull the pendulum away. As long as we keep a small angle, our period is going to be independent of these things. And then lastly, we have the definition of a wave, which is going to be an oscillation that propagates, or we could say a disturbance that travels. And we have to remember here that waves are going to transfer energy, not matter. Alright guys, next we're going to be talking about the different types of waves. So first off, we have mechanical versus electromagnetic waves. With mechanical waves, we're actually going to need a material to propagate the wave. So these could include sound or earthquakes. And with electromagnetic waves, we don't require matter in order to propagate. So this could include light or radio waves. Furthermore, we're going to have longitudinal versus transverse waves. With longitudinal waves, our oscillation is going to be parallel to the direction of travel, like sound. And with transverse waves, our oscillation is going to be perpendicular to the direction of travel, like all electromagnetic waves. So we have an image here on the right in order to kind of see the differences between longitudinal and transverse waves. So on the top, we see that our oscillation is actually going to be horizontal, and our motion is also going to be horizontal. So in this case, we have an oscillation that's parallel to our motion, so we know this first case must be longitudinal wave. Next, we have a wave that has an oscillation that moves up and down, and we see that our motion is going to be left to right. So here we have an oscillation that's perpendicular to our motion, so therefore here we must have a transverse wave. So with longitudinal waves, it's a little difficult to visualize the actual wave. So in this scenario here, we now converted this wave into sort of a sine-cosine graph based upon the density within this material. So we can see in this spring, in this area for instance, we have a very high density. The spring is very compressed, and that's what we can see here on this graph below. Then in this area we see that the spring is less tightly packed, so therefore we have this lower density here. And basically by graphing the density of this spring, we're able to get this sort of sine-cosine wave look. This brings us into periodic waves. So every point or particle is going to move in simple harmonic motion, and the interactions between adjacent particles are going to provide the restoring force, and the energy transported is proportional to the amplitude squared. or a squared. And our frequency, which we're going to denote as a lowercase f, is going to be the number of waves per unit of time. Our amplitude, or capital A, is going to be the height of a wave measured from the middle position. So basically, this would be our amplitude here. We go from the middle position and to the top of the wave. Our wavelength is going to be the distance between two equivalent points within that wave. So basically, if we were to choose this point and this point, which are equivalent, then this would be our wavelength. Alright, next we'll be talking about the wave equation, which we're going to call velocity is equal to our frequency times our wavelength. And basically an important thing to realize here is that our velocity is actually not dependent upon frequency or wavelength. It's dependent upon the medium which the wave is moving through. What we really want to conclude here from this equation is that when we change our frequency, our wavelength is going to also be affected by that. So basically, if we were to increase our frequency, our wavelength would shorten, and if we were to decrease our frequency, our wavelength would lengthen. And this brings us into wave speed. So like we said before, the wave speed is going to depend upon the medium. So for a string, the wave in a string is going to have an equation equal to this. Velocity will be equal to the square root of our tension force over mu, and mu is going to be equal to our mass over our length. And here's just two wave speeds which are a little important to remember here. We see that the speed of sound in air at 20 degrees Celsius is going to be equal to 342 meters per second. And the reason why we state a temperature here is that when this temperature increases for the speed of sound in air, the actual speed of sound will increase as well. So we want to make sure we are very clear in stating that this is at 20 degrees Celsius. And then similarly for the speed of light in either vacuum or air, because for the speed of light it's going to be very similar between vacuum and air, we see that our speed of light is going to be equal to 3 times 10 to the 8th meters per second. We can see that there's a big difference between the speed of sound and the speed of light, which is much faster. This brings us into interference, which is basically when we have two or more waves at the same location and same time. And an important observation we can make here is that they're going to pass through and proceed unaltered. So basically they're going to have their point of interference. We're going to see what happens in a little bit, but then after they interfere, both waves are going to move on as if nothing had ever happened. And this brings us into the principles of superposition, which states that the combined waveform of two or more interfering waves is given by the sum of the displacements of each wave at each point. So basically, in order to find what happens during our interference, we're going to take our displacements of each wave involved with the interference, and we're going to simply add them. We're going to have to make sure to look at our not only our magnitudes, but also the direction of our displacement. So for instance, if we had a positive and a negative displacement, these could potentially cancel each other out. And this brings us into constructive interference, which is when we have displacements that are in the same direction. And this could possibly lead to total constructive interference, which is basically when we have two waves which have the exact same amplitude that are going to interfere with one another, having the same displacements in the same direction, and this would actually make their sum equal to 2 times the amplitude of one of the waves. So basically we're going to double the amplitudes of the waves at this point of interference. Then we also have destructive interference, which is when our displacements are in opposite directions. And this could potentially become total destructive interference, which is when we have the same exact waves as far as magnitude goes, but their displacements are in opposite directions. So when they interfere, their displacements are actually going to cancel out and give us a sum of 0 at this point of interference. So basically, I'm going to draw a line down the center here. Everything to the left is going to be an example of constructive interference. So we see here, we start off with two waves which are moving towards each other, and we can see that both waves are in the positive direction. We see that their displacements are in the same direction. So when they come together, we see here, it still seems as though they're retaining their shape. Here at this point, where is the actual point of interference where they're meeting right directly in the middle, we see that the amplitude here is going to be much greater than either of the waves before, and that's a common thing with total constructive interference. We're going to increase our amplitude of our waves at this point of interference. But then what's important to realize is after the waves continue away from this point of interference, we see that we once again have our initial waves, and basically the waves are going to act as if nothing had happened to begin with, which is what we made. We made this point over here that they're going to pass through and proceed unaltered. So really the only difference is going to be at the actual point of interference. So everything to the right of this line is going to be an example of destructive interference, which is when our displacements are in opposite directions. So here we have sort of this larger wave on the positive side of the rope, and then a smaller wave on the negative side of the rope. And when these come together, we see that our amplitude actually greatly decreases, and the reason for this is because we have waves which are facing, the displacements are facing in opposite directions. So basically, we still have a somewhat positive amplitude, and the reason for that is that our initial amplitude was greater on the positive side than the negative side. And then once again, after our actual point of interference has occurred, we see that both waves are going to continue moving as though nothing has happened. Alright guys, next we're going to be talking about reflection, which is basically when a wave strikes the boundary of a medium and is partially diverted back into the medium. So common examples of this would be an echo or a mirror, and when we're talking specifically about strings, when we have a fixed end, it's going to reflect the opposite of our wave, and when we have a free end, it's going to reflect the same wave. So we can see that here on these images. In this first one, we have a fixed end, so we know in this case it should reflect the opposite, which it does. We can see here we have a certain amplitude of our wave here, and then after being reflected, we see that we have sort of the opposite amplitude and direction of our wave. And then over here, we see that we have this ring structure that the string is attached to, and basically this ring is able to move up and down the rod as it pleases. So as the wave comes towards the end of the medium and is reflected, it's going to have the same amplitude and direction as the initial wave. And this brings us into standing waves, which is basically when we have two waves that have both the same amplitude and the same frequency and are within the same medium, but they're moving in opposite directions. And basically we covered this before when we talked about total destructive interference, which is what causes these nodes to appear, which are points that are not moving. And then we also have antinodes, which are going to be points that have maximum movement. So an example of this would be guitar strings, and we could see here we would have our node, and here we would have our antinode. And this brings us into string again. When we have a string that's fixed on one end, it's going to create a node, and then one that has a free end is going to create an antinode. And this brings us into sort of our harmonics. When we have a scenario where we have a string at both ends being fixed, we're going to want to use this equation here, and we're going to plug in values for n like 1, 2, or 3. And for instance, if we were to plug in 1 for n, it would give us our fundamental frequency, or our first harmonic. If we were to plug in 2, it would give us our second harmonic, also called the first overtone. And then for a string that's fixed at only one end, which isn't as common, but we still need to know what happens, we would want to use this equation here, and we would plug in values for m like 1, 3, or 5. We would want to skip our even values, and basically when we plug in 1, we're going to once again get our fundamental frequency. When we plug in 3, we would get our third harmonic, and so on. Alright guys, that's going to wrap it up for this video. Thanks for watching.